A cylindrical elastic body subjected to pure torsion about its axis develops. The options are tensile stress in a direction 45 degrees to the axis, no tensile or compressive stress, maximum shear stress along the axis of the shaft, maximum shear stress at 45 degrees to the axis. This question is being asked in 1989 GATE question paper for round mark. Actually, a cylindrical elastic body means we can take it as a shaft, cylindrical shaft. Subjected to pure torsion means pure rotation. Okay. In such a case, we can consider a point on the shaft which can be represented by this diagram. Here you can see tau refers to the torsional shear stress developed due to pure torsion. Okay, there will be only pure torsion. You can see there will be no normal stress acting on the shaft. Okay, due to this torsion, we can have tensile stress and shear stress. Okay, these two are called planes of pure shear or plane of zero normal stress or plane of maximum shear stress. As you can see, these are concepts under principal stress. We can see that sigma x plus sigma y is equal to 0. There is no normal stress here, but due to this pure torsion, we are having tensile stress and compressive stress, which sums up to be 0. Sigma 1 is equal to minus sigma 2 refers to major principal stress is equal to negative of minor principal stress. That is, tensile and compressive stress exist, which are of same magnitude equal to the shear value, torsional shear stress. Okay, this plane is called, these two particular planes are called fracture plane for MS shaft. Why particularly for mild steel? Mild steel is a ductile material. Ductile materials fail in shear. They don't fail in tension. They fail in shear. Okay, so this is the fracture plane. And these two are called principal planes, and the stresses acting on those are called principal stresses. Now you can see that tensile stress is acting at 135 degree to this face. So when you consider an axis which is perpendicular to the paper, you will be getting 45 degree. That is, you will be getting 45 degree in this angle. 45 degree. So tensile stress in the direction 45 degree to the axis is developed. The three-dimensional state of stress at a point is given by sigma is equal to, and the values are given. The value is denoted by the unit meganewton per meter square, and the shear stress on the x phase in y direction at the same point is then equal to. They have asked the shear stress on x phase in y direction. And the options are given as 0, minus 10, 10, 20. It is a 1990 GATE question offering 2 marks. Okay, what is a stress tensor? Actually, the matrix representation of the state of stress at a point is referred to as stress tensor. And if it is for 3D, 3 dimension, it is referred to as 3-dimensional stress tensor. So sigma 3D is equal to the values here correspond to these denotions like sigma x. Sigma x refers to normal stress in x direction. Sigma y refers to normal stress in y direction. Similarly, sigma z is on z direction. Now tau xy refers to the shear stress on x phase in y direction. The first value denotes the phase in which it is acting, and y denotes the direction in which it is acting. Similarly, tau x z denotes the x phase and z direction. It is a symmetric matrix where you can see tau xy is equal to tau xy, and tau xz, tau xz. Actually, it is a symmetric matrix. Here you can see 10, minus 10, 20 and 10, minus 10, 20. So by just comparing, you can find the shear stress on x phase in y direction. Shear stress on x phase in y direction corresponds to this value, tau xy. So here it is 10. So the answer comes out to be 10 meganewton per meter square. If it is asked as shear stress on y phase in z direction, then you should go for tau yz. Y phase z direction. So you will be getting 20 meganewton per meter square as the answer. If in case they ask a question like tau in y phase in x direction means you are reversing the direction. So instead of tau xy value, if it is 10, you just have to add a negative sign and find the answer. So minus 10 comes out to be the answer for shear stress acting in x phase in y direction. This is a simple comparison by which simply just comparing and finding the value, you can get 2 marks. A rod of length L and diameter D is subjected to a tensile load P. Which of the following is sufficient to calculate the resulting change in diameter? They have asked which of the following, these are constants. Which of the following constants is sufficient? They have asked the sufficiency and not what are all required. Sufficient to calculate the resulting change in diameter. Okay, now we are given answers as Young's modulus, shear modulus, Poisson's ratio, both Young's modulus and shear modulus. It is a 2008 simple one more question. Generally, for uniaxial tension, change in length is given as del L is equal to PL by AE. This is a normal formula for, a general formula for change in length. Similarly, change in diameter can be calculated using this formula minus mu of the longitudinal strain, because diametral change occurs in the lateral direction. This is longitudinal and this is lateral. So lateral is calculated. Lateral change in the dimension is calculated as minus mu into del L by L. So del D by D will be there. So D comes here and it gets minus mu into del L by L into D, where mu refers to Poisson's ratio and E refers to Young's modulus. So our answer has to be E and mu are sufficient to calculate. But Young's modulus is given separate and Poisson's ratio is given separate. But here you have been given as Young's modulus and shear modulus. Okay, there are relations between these constants, including bulk modulus also there are relations. So just by knowing these two values, you can calculate mu and you can substitute here and you can find the resulting change in diameter. There is a general factual point that for an isotropic material, generally in engineering, that is in strength of materials, we consider isotropic materials only. So in such isotropic materials means they will be having constant elastic properties in all directions at all points. So the number of independent elastic constants in case of an isotropic material is 2. So if there are Young's modulus and shear modulus, that is sufficient. If it is Young's modulus and Poisson's ratio, that is sufficient. If it is shear modulus and bulk modulus, it is sufficient. So here there are 2 and so we consider D as the answer. A rod of length L having uniform cross-sectional area A is subjected to a tensile force P as shown in the figure given below. If the Young's modulus of the material varies linearly from E1 to E2 along the length of the rod, the normal stress developed at the section SS is. In this section, they are asking the normal stress developed due to this point load called P, which is a tensile force. Okay, generally stress depends only on the force applied and the area in which it is acting. At this point, you will be having a parabolic variation of the stress, but at a fiber, that is that at a cross section SS far away from this, you will be having a linear variation. That is, P by A will be constant at all points here. So stress depends on the force and the area and not on the modulus of velocity. That is not on the material property. So sigma is equal to P by A is the answer. Such large questions will be asked to confuse us with the basic concepts, but it is a basic knowledge that stress depends only on the force and the area on which it is applied. So it is given as 1 mark. Though it seems bigger, it is offered 1 mark. From this you can understand that it is a simple factual knowledge. So P by A is the answer. A circular rod of length L and area of cross-section A has a modulus of elasticity E and coefficient of thermal expansion alpha. One end of the rod is fixed and the other end is free. This condition is called a free expansion condition. If the temperature of the rod is increased by del T, by a difference of del T, then they have asked what will be the stress and what will be the strain. Such question is being asked in 2014 gate question paper in set 1 for 1 mark. Okay, let us understand what are the three conditions possible in thermal expansion. First, it is free expansion. In free expansion, there will be thermal strain. Always in case of thermal expansion, we will be having thermal strain as alpha del T, which is tensile. But if it is free to expand, then there will be no longitudinal strain. As a result, there will be no thermal stress. Thermal stresses are due to this longitudinal strain and not due to this epsilon thermal, that is thermal strain. This thermal strain is restricted, means then we will be getting a longitudinal strain which is responsible for a thermal stress. Okay, completely restricted expansion in one direction refers to a bar held between two rigid supports. In such a case, there is no expansion permitted. So there is restriction for this alpha del T. So there is a negative thermal stress, which is epsilon longitudinal. This negative thermal strain comes out to be a thermal stress of compressive nature. Similarly, in the case of partially restricted expansion in one direction, that is, one end of the rod is rigidly held while the other end is free to expand for a small value, that is, the other end of the rod is at a particular distance from a rigid support. In such a case, there will be thermal strain, but due to this thermal strain and due to the restriction at a particular distance, we will be having a longitudinal strain of this value. This corresponds to a thermal stress, this value. Here it is free expansion. From free expansion, we know that the thermal stress is 0 and the thermal strain is alpha del T. Here the answer which corresponds to this is stress developed in the rod is 0 and strain developed in the rod is alpha del T. So C comes out to be the answer. Okay, the stress strain curve for mild steel is shown in figure given below. This is the stress strain curve given. Choose the correct option referring to both figure and table. You have to compare these two and find the answer. It is actually like a match the following answer. So, a simple way of answering this is, first we have to find which particular value, I mean P, Q, or S, T, U, among these, which has different values in all the four options. Here you can see it is 1, 3, 3, 4, 2 times 3 is repeated. Here 2, 1, 4, 1, 2 times 1 is repeated. 3, 4, 1, 5. All the four values are completely different. If you know what R corresponds to, and for example, for this point, R is called upper yield limit. That is upper yield point. Upper yield point. So R is 1. If you confirm this, and you can confirm that C is the answer, and you can check other values and you can go for it. This is a simple way of answering a match the following question. Okay, now let us learn about this stress strain curve. This part is being elaborated here, magnified here. Here you can see P. P refers to the proportionality limit in a stress strain curve. Proportionality limit is the point up to which the curve is linear and Hooke's law is valid. Hooke's law means sigma is directly proportional to epsilon. That is, normal stress is directly proportional to the longitudinal strain in that particular direction. So, P refers to the proportionality limit up to which Hooke's law is valid. And then Q refers to, here it is a slight curve. This point is called elastic limit up to which the material behaves elastically. And beyond that, R is called the upper yield point. The point after which the material begins to yield, that is, the material begins to plastically deform. S is the lower yield point. S is the lower yield point. And after this, we will be having yielding, and then we will be having strain hardening phase. This is called strain hardening phase because for increase in strain, the stress will be increasing. So it is a strain hardening phase, and this is strain softening phase. This T is called ultimate tensile strength. It is the maximum strength that the material is capable of handling. That is, it can bear without breaking. This is the breaking point or fracture point. That is the failure point where the material completely breaks. Okay, these are the points in a stress strain curve. Okay, corresponding to this, as we can see, R has different values and T has different values. So first we will be considering for R. As said earlier, R corresponds to the upper yield point. So R is 1, and now you can check P, P3 proportionality limit, Q4 elastic limit, and R1 upper yield point, and S5 lower yield point, T2 that is ultimate tensile strength, and U is 6 failure. So C is the answer. Which one of the following types of stress-strain relationship best describes the behavior of brittle materials such as ceramics and thermosetting plastics? It is not just brittle materials, they have specific ceramics and thermosetting plastics. These are type of plastic materials. Sigma refers to stress and epsilon denotes strain. First, let us know what are perfect brittle materials. Perfect brittle materials exhibit little elastic deformation. They break suddenly, like this. They break suddenly. Here also they break suddenly. For perfect rigid materials, the strain is zero. So the line comes out to be a straight line similar to the y-axis. So this curve corresponds to a perfect rigid material. And for perfect elastic materials, only elastic deformation. Here you can see only elastic deformation. So this is perfect elastic material. Also for perfect brittle materials, there is only elastic deformation and there is sudden breakage. There is no plastic deformation. So this curve also corresponds for perfect brittle material. So this curve is for perfect brittle material and perfect elastic materials. They haven't asked perfect brittle materials. They have asked thermosetting plastics. So there is plastic deformation and there is no elastic deformation, and finally they break suddenly. So the answer corresponding to this question is answer C. But if they have given just behavior of perfect brittle materials or just behavior of brittle materials, this will be the right option. And what is this? This is called a material which exhibits elastic property with linear strain hardening. As we discussed earlier, for each increase in strain, there is increase in stress. So it is strain hardening. Elastic material with linear strain hardening. This corresponds to a rigid material. This is linear material, that is elastic material with linear strain hardening. This corresponds to a plastic brittle material if it is plastic, and this corresponds to a perfect brittle material and a perfect plastic material. A square plate of dimension L cross L is subjected to a uniform pressure load P, that is 250 megapascal on its edges as shown in the figure. Assume plane stress conditions. Plane stress is referred to as biaxial state of stress. The Young's modulus E is 200 gigapascal. It is a 2016 2 marks set 3 question. Okay, the deformed shape is a square of dimension L minus 2 del. Here it is a del and here it is a del. And if L is equal to 2 meter and L is equal to 0.001 meter, the Poisson's ratio of the plate material is being asked. It is a numerical question. So it is a biaxial state of stress. Generally, we know for longitudinal strain, the formula is change in dimension by original dimension. Change in dimension is given as final length minus initial length. Final length is L minus 2 del, which is the deformed shape refers to the final length. And the initial dimension is L. So L minus 2 del minus L by L, which gives minus 2 del by L. Also, epsilon x, that is longitudinal direction in horizontal way, horizontal direction is calculated as minus P by A refers to the compressive stress created due to this compressive load. So sigma by A. P by A refers to sigma. So it is minus P by AE plus why it is plus? Because mu comes with a negative sign. Minus into minus of mu. So it will be plus mu into P by AE. P by A is the stress, which is tensile stress, because here it is compressive, which will be multiplied by a negative and gives you a tensile stress. P by AE plus mu into P by AE. So by relating these two, that is minus 2 del by L is equal to minus P by AE plus mu into P by AE. Just substituting these values, you will be getting the Poisson's ratio. But here they haven't given the area on which this load is acting. So we can consider the area to a value of 1 square meter, that is 1 meter square. So by neglecting A and A, we will be having minus P by E plus mu into P by E is equal to minus 2 del by L. Del is being given, L is being given, P is being given, and E is given. By just substituting the value, we will be getting this value as 0.2. If in case they have given area, you include the area and you have to calculate. A horizontal bar fixed at one end x is equal to 0 has a length of 1 meter and a cross-sectional area of 100 millimeters square. Its elastic modulus varies along its length as given by E of x is equal to 100 e power minus x gigapascal. It is a varying elastic modulus and it is not constant, where x is the length coordinate in meter along the axis of the bar. An axial tensile load of 10 kilonewton is applied at the free end x is equal to 1, which is meter. The axial displacement of the free end is, they are asked the elongation. Generally, the formula is change in length of a small strip of length dx. That is, we are considering a small portion of that bar and we are finding the change in length, which corresponds to P into dx by AE. P, A, E are the values at that particular cross section. So total change in length of the bar is given just by integrating. So del total is equal to integrating from fixed end to the free end of 1 meter. P into dx by, this is meter, so all values should be represented in meters. We know that the load is constant and the area is constant. So P is here you can see as 10 kilonewton, so it is 10,000, and area you can see as 100 millimeter square. So this comes out to be 100 by 10 power 6 gives the value in meters. So 100 by 10 power 6, and here it is 100. This is taken out, and it is in gigapascal. So 10 power 9 constant is being taken out. Here we are left out with e power minus x, which comes out to be e power x into dx. Just by integrating, we will be getting 1 by 1000, and by simplifying, we will be getting 1 by 1000, and by integrating, we will be getting e power 1 minus e power 0. E power 1 value is 2.7183. E power 0, anything power 0 will be 1, so we will be getting 1.7183 divided by 1000 meter. Here it is asked in millimeters, so 1 by 1000 is neglected and we have the answer as 1.7183 millimeter. Such type of integrating questions, we must learn the basics. The principal stresses at a point in a critical section of a machine component, or machine component can be anything, are sigma 1 60 megapascal, sigma 2 5 megapascal, and sigma 3 minus 40 megapascal. These three are principal stresses. For the material of the component, the tensile yield strength, that is SYT, yield strength in tension, is sigma y is 200 megapascal. It is also denoted as SYT. According to the maximum shear stress theory, the factor of safety is, what is maximum shear stress theory? By maximum shear stress theory, the absolute maximum shear stress must be lesser than or equal to the shear strength in yield, that is strength of the material in shear, okay, divided by factor of safety. According to MSST, SYS and SYT, that is yield in shear and yield in tension, both strengths are related by this formula. SYS is equal to SYT by 2. So the absolute maximum shear stress is determined likewise sigma 1 minus sigma 2 by 2, that is difference between the first two principal stresses divided by 2, and difference between the next two principal stresses divided by 2, and difference between the first and last principal stresses divided by 2. By this you will be getting the maximum, absolute maximum. What absolute maximum is important because there are two types of maximum shear stress, that is in plane maximum shear stress and absolute maximum shear stress. Here we are concerned with absolute maximum shear stress. So maximum of these three values is taken and it is compared with SYT by 2 instead of SYS, SYT by 2 N. So according to maximum shear stress theory, they have asked N. So we will be getting 2 to cancel. So here the maximum value, as you can see, 60 minus 40, it will be the maximum. 60 minus of minus 40 will be giving 100 and SYT is 200. So N comes out to be 2. So is the answer.